Hi everyone, welcome to APCTP String Seminar. It's great pleasure to introduce our speaker Akhil Sivakumar from ICTS, India. He is a PhD student in ICTS and he will finish PhD soon. Today he will talk about the fluctuating hydrodynamics via holography. Please join me in welcoming our speaker Akhil.
So shall I start? Yeah.
Sure.
Yeah. So thank you all for this opportunity to speak at your group. So I wanted to talk to you about give you an overview of the couple of projects we have been doing over last few years, last couple of years, and it's a paradigm, it's a perspective on general real-time ADA-CFT physics, where especially when there's a black hole involved in the bulk and so on, where you think of like the CF and understanding the boundary theory as some open system, or or understand the boundary theory input as a path which affects the dynamics of an open system and so on. So in particular today I'll talk about understanding the hydrodynamics in this open theory, effective theory language. So I'll mainly talk about this first. So you guys can also see my cursor.
Yes.
Okay, thanks. So I will be mainly talking about this work here, which we put out last year with Joel Ghosh, who was a postdoc in ICTS, and now he has moved to Dhaka University as a faculty. Loganayagam, who is my advisor. Siddharth Prabhu, who was our postdoc and has now recently moved to TFR Mumbai. Mukund Rangamani, who's a faculty at UC Davis, and Vishal, who is also a postdoc with us. And then there's this ongoing work which should appear sometime soon, which is again with Joel, Loga, Mukund, and Temple Hay and Julio Virueta, who are postdocs at UC Davis. So let me start with an introduction. So we know fluid gravity correspondence maps long wavelength deformations of dual blackbranes to long distance excitations or hydrodynamics of holographic plasmas. So the original fluid gravity program analyzes quasinormal excitations of the blackbranes. Then the conservation of boundary stress tensor, which when written in a fluid appropriate way and so on, then gives the equational motion for the boundary fluid. To summarize, over large distances, the plasma, you can show from holography that the plasma behaves like a dissipative fluid governed by a Navier-Stokes equation. So one way to interpret this result is that using holography, you can understand the hydrodynamic limit or the long distance behavior of a strongly coupled theory. And as is familiar since the days of holography, since ADA-CFT, this kind of sets our expectation out of any strongly coupled system and how it should behave and so on. But when viewed from the bulk side, it gives us a way to think of slightly deformed black hole solutions, which are not the equilibrium black hole configurations, or slightly deformed black hole solutions from as configurations of a fluid by mapping the Einstein's gravity solutions or the black hole solutions to the configurations of a fluid. But then it is known that dissipative fluid description is only an approximation to the more complete picture of fluctuating hydrodynamics. So the reason for this is that once you see there's a dissipation, which means there's energy being dumped into some microscopic degrees of freedom, the same microscopic modes which cause dissipation also affect the hydrodynamic description as stochastic forces. So this is evident from the statement of fluctuation dissipation relation, which says if you have a dissipation constant, there is a noisy force, and the noise at leading order is Gaussian with its variance related to the dissipation constant and so on. In addition, you realize that once you study hydrodynamics and then trying to make it consistent theory, like a statistical theory of hydrodynamic modes, you realize that in addition, there are statistical fluctuations of the hydrodynamic modes itself, which are long-lived modes, which have to be correctly accounted for. And this fact kind of makes your theory sick. To explain, one of the assumptions you make while passing on to hydrodynamic description is that you have a field theory that has microscopic fluctuations, but many of these microscopic fluctuations in fact die down fast, decay fast. And if you decide to coarse grain enough over longer distances, you can go to a fluid description where these microscopic fluctuations can be averaged out, and you can look at the behavior of long-lived modes like conserved charges and so on. And that's how you go to hydrodynamic description. But then once you reach hydrodynamic description and start realizing that there are statistical fluctuations of the hydrodynamic modes itself, it says there are long-lived fluctuations. And this is the subtlety about understanding fluctuating hydrodynamics, that it makes the theory itself sick. And once you start accounting for these fluctuating hydrodynamic modes and so on, it kind of makes the hydrodynamic expansion in terms of some fluid velocities and some fluid-like notions. It kind of makes it invalid. So this is a basic premise of my motivation for correctly understanding fluctuating hydrodynamics. And this sickness I'm talking about is has been well known in non-relativistic fluid dynamics. And you can look at this paper for a discussion where they argue that the same should be true for relativistic fluid dynamics. So to understand the kind of picture we are motivating, to understand the fluctuating hydrodynamic theory, it's useful to look at a toy model. So consider probing a fluid with a particle, say a pollen moving through some air or something. At low energies, we see only hydrodynamic modes, which is sound, pressure, waves, and so on. The presence of microscopic modes, like molecules, is diagnosed from the fact that the probe you introduced, the Brownian particle, shows Brownian motion, as in the diagnosis for the molecules is that there is Brownian trajectories of the particle. And the lesson we have to take away is that the low energy description is an open FT theory of the hydrodynamic modes and probes interacting with microscopic modes. In other words, the fluid has fast relaxing degrees of freedom, which I call Markovian, and long-lived or long-scale correlating modes correlated over long scales, which I call non-Markovian modes. To get a long-distance effective description, we may integrate out the fast Markovian modes while retaining only the slow non-Markovian modes of the fluid. And you have to retain the slow non-Markovian modes because these degrees of freedom are long-scale correlated, and you want a local effective description and so on. You don't want to integrate them out. So then the objective of a program is to derive such a Wilsonian open EFT. It's called Wilsonian precisely because you integrate out the fast or short scale fast modes or the short scale modes and retain only the long scale modes.
So here, when you say open, does it because this microscopic mode is kind of outside of your system, or
right? There are a couple of ways it is open. One is that you integrate out microscopic modes, and then think of only probes coupling to them, and then how the microscopic modes affect the probes, and that part is open. But there's a second way in which it is open in the sense that it's already, the system is at a temperature, right? Even the fluid, when you say it's at a temperature, it is like there is a fictitious bath coupled to it, which is maintaining that temperature and so on. So in that sense, it is open. So if you look at holography or something, the black hole has some microstates and so on, which you don't really talk about. So the fluid is open in that sense. So it is in some level it is microscopic modes, but there are two levels of openness I'm saying. Like one is the short scale modes in the bulk itself, which you don't say in the holographic example, the short scale modes in the bulk itself. But then even when you study gravity, you will see that gravity, which is massless excitations, which in the low energy limit, But even then, you will see that the fluid degrees of freedom don't involve all the gravitational excitations, but only a part of it. So there are two levels of indicate like openness. Yeah.
So for in the Wilsonian RG, you also integrate out this high frequency mode, or so there we don't call it the open.
Right, because there you are integrating out high frequency stuff, like you said. But here
it's not just integrated out; it's more than that.
It is here. It is like you indicate out excitations which are triggered at the same energy level, but it's just that these energies, these excitations don't have long scale correlations. Like it's like saying, like, I mean, if you introduce a particle into the, or like if you, it's not like if I like create sound, I don't excite any air molecules at all. But like my description doesn't really like analyze at the level of air molecules, but it kind of averages out and thinks of the fluid description of the air. So so the openness comes from the fact that the stuff you integrate out are excited at the same energy levels as you're probing. Unlike in the usual renormalization or something where you think the things you integrate out are like really high energy modes, the low energy dynamics doesn't even care about it. Here it's more like a real coarse graining. Yeah.
Thank you.
Sure. Thanks for the question. So having motivated the Wilsonian EFT perspective for fluctuating hydrodynamics, there are two technical questions to answer. Given a model, the first is that given a model, how do we separate out slow modes from fast modes and selectively distill them out? Which is the point I just mentioned, that there are, even if you don't think about the microscopic deep brain configurations or whatever, but like even if you start from the gravity perspective, the entire boundary fluid dynamics, by fluid dynamics I mean the non-Markovian part, which I defined as the part which has long range correlations, does not dualize to the entire bulk graviton dynamics. There's part of the bulk graviton dynamics which still leads to only short scale correlation in the boundary. But then there's part of graviton dynamics in the bulk which will give to long range correlation, and same for any gauge field over all that. So I've been concentrating on graviton dynamics because I'm assuming like all of you guys are like familiar with ADS-CFT, and then graviton dynamics dualizes to stress tensor dynamics of the boundary, right? Which is part of the energy pressure waves and all that. This talk, in first half of this talk, I'll motivate a formalism which does the separation, and the way I motivate it will be evident that at least for holographic systems, this way of looking at it should work. The second question is that how do we incorporate the effect of statistical fluctuations, right? So the field theoretic formalism to analyze real-time dynamics and hence fluctuations and so on are known as Schumann-Keldysh path integrals. These are some modified path integrals which, unlike the usual path integrals we are more familiar with, don't track the evolution of some initial state to final state, but they track the evolution of density matrices or mixed states rather than pure states. And in holographic models, boundary statistical fluctuations are dual to Hawking radiation from the bulk blackbrane. So the statistical fluctuations in the boundary are like really in the holographic way to look at it are like really triggered because the black hole is like in the bulk, they are like dual to the bulk quantum fluctuations, which says that the black hole really triggers Hawking radiation, which at the leading order we know is thermally populated and so on. And that's how, in fact, holography realizes there are boundary fluctuations which are thermally populated. Therefore, we require a systematic procedure to incorporate Hawking modes in the bulk, which you would know is like a subtle thing, because like at the horizons, it's confusing what boundary conditions you impose and all that. So the summary of this is that to correctly study the statistical fluctuations of the boundary, in our case, the fluid modes and so on, we need to carefully study the Hawking radiation in the bulk, And as you go forward and account for interactions and so on, like you have to understand how the dissipative excitations of the fluid, which in the bulk becomes quasi-normal modes, like I said in the last slide, which go into the black hole, dissipate energy. And then the fluctuations sourced by the bath or the black hole are the Hawking radiations triggered by the black hole. And how these guys interact, how they scatter, and all that. So we need to correct, cleanly and very carefully turn on Hawking modes in a field theory consistent way, and such that these effects can be cleanly studied. And then from this perspective, I said like that either you can think of fluid gravity as studying the strongly coupled fluid dynamics as a gravity problem, or this also gives you a way to think about deformed black hole solutions as fluid fluid configurations. Implementing this fluid gravity program to the full level of fluctuating hydrodynamics now gives you a way to understand the strongly coupled fluctuating hydrodynamics as black hole dynamics, but with Hawking effects. And then you also now have like a way to think about Hawking reacting black holes, where the Hawking and quasi-normal modes and all interact like the way I said, as fluctuating hydrodynamic configurations. Sorry. So this is the general perspective of this project. And maybe I can stop for a second for questions.
I have a question about this Hawking mode. So usually Hawking mode is maximally entangled with the black hole or some particle, each particle inside. Here, do you have such a kind of feature, or here because of
not really, not really, because we don't. So you'll see that the way we turn on. Okay. Maybe the question is not really, and maybe a bit, in the sense that one thing is that we from the beginning we pass on to some like Schwinger-Keldysh like formats, which since like it's a double setup, and you consider a double black hole. So, and the analysis is at that level fully classical. You don't do any bulk quantum calculation, or we don't think about some very fine-grained gadgets like entropy or something. We just do a classical analysis of the excitations in the bulk. But in the sense in which it is maybe it has some of it, is that like you kind of forget about the interior, but the interior is replaced by another second copy of the outside. So in this sense, it is morally similar to the thermofield double or the eternal black hole picture, where you capture the thermality as entanglement with the second copy, but not really, because here you don't think of this second part as a second copy, but it's just as the bra part of the Hilbert space itself. There's a Ket bra Hilbert space kind of, because it's a density metric state. So I don't know if you should think of it as really yeah. So it is evident that the Ket evolution in the blackbrane geometry will affect the bra evolution in the blackbrane geometry, but I mean, if I understood your question correctly, we don't really try to make the connection of this connection as something non-trivial about the interior or something, or we don't even really we haven't really thought about any of the fine-grained gadgets like entropy or something, but appropriated to the kind of techniques we use. By that I just mean the Schwinger-Keldysh configuration of the blackbrane, which I'll explain what I mean by that. So, so the answer is maybe. I don't have anything very clear to say about it. Okay. So if there are no more questions, I will start so this outline. I'll give you a summary of how we think about distilling out fluid modes, that is separating fast and slow modes. Then I will motivate what we call the Wilsonian boundary conditions, which is an alternate boundary condition. Than alternate boundary condition to the usual GKPW boundary conditions of ADS-CFT, and we say why this is the correct. I will kind of motivate why this is the why there's such a change in boundary conditions is required to implement the Wilsonian EFT paradigm I was motivating. Then I will give a lightning introduction to Schwinger-Keldysh path integrals, and then also use motivate the bulk setup we use. the gravitational way to implement such a path and vector. Then we will briefly look at if there's enough time, we'll look at this a toy model of nonlinear Langevin equation, which you can derive from holography using this kind of techniques, and which is useful to interpret the kind of things I'm saying. Because at this moment I'm talking about some open FT field theory and Schinger-Keldysh field theory and so on. But the Langevin equation is something we understand. We understand it as some description of particle with some noise and so on. So it's useful to look at this to kind of make sense of what this program is trying to achieve. And then I'll summarize and plot some future directions. Okay. So let's talk about distilling or fluid modes. So like I motivated, we need a general prescription to separate out Markovian and non-Markovian dynamics. So I'm focusing on a d-dimensional CFT. The working principle seems to be to implement an SO-d-2 harmonic decomposition. So what I mean by is that you go to a picture where there's a CFT D and then there are d-1 spatial directions. And you go to a picture where each hydrodynamic mode is labeled by its wave vector. So it's a chosen direction among the d-1 spatial directions. And then you look into what is the representation of the transverse SO-d-2 rotations into which this mode folds, right? So this is similar to how we think about particles in the Wigner-Little group framework. You fix a momentum and then you think about what keeps this momentum fixed. So here you fix a wave vector and then you think about what is the transverse, what kind of transverse rotations keeps this momentum fixed, and classify hydrodynamic modes according to or the general excitations of the boundary in terms of this SO-d-2 decomposition. So this is a setting of notation. There are tensors of this decomposition and vectors of this decomposition and scalars, and so many of them denoted by sigma and alpha. So the one reason this is plausible is that for general manifolds of type M2 times SD-1, where 2 and D-1, so this I'm talking about bulk. Okay, so general manifolds of type M2 times SD-1, where 2 and D-1 denote the dimension, and the S is maximally symmetric. Then you can show that this separates Einstein or Maxwell perturbations in the bulk to gauge invariant sectors. So the motivation here being that if the Markovian and non-Markovian dynamics should be separately gauge invariant. So one keyword to lead you in this separation is that since these are dynamics of different time scales and you're integrating one out and so on, they should be separately gauge invariant. And why Einstein and Maxwell? Because like I said, we are interested in the hydrodynamic limit. We are interested in some conserved currents and stress tensor or some conserved charge currents and so on in the boundary, and which dualize to the bulk Einstein and Maxwell perturbations. So to be more explicit, like I said, you can take a U1 current, J mu, and then the spatial part of the current can be decomposed into this SO-d-2 harmonics. There's a vector and a scalar gradient and so on of the current. And you see that since it's SO-d-2, it is transverse, which means that it has vanishing divergence. So in some sense, this spatial current is trivially conserved. Which means that it couldn't have done anything non-trivial. It couldn't have done any long-scale, non-trivial physics, which we expect is to be diffusion and so on. Which you in fact you can show that only JS leads to non-trivial long-scale behavior, and it leads to charge diffusion and so on. Similarly, you can decompose the stress tensor, the stress, into SO-d-2 harmonics. You will get scalars and vectors and tensors. And the tensors, since again they are transverse, are trivially conserved, and they couldn't lead to any non-trivial dynamics. So they are again fast modes. So the point is, since VA and TIJs are trivially conserved parts, they lead to fast dynamics, which they lead to Markovian dynamics. And TV and TS part here are not trivially conserved, and hence they could do something non-trivial, which they do. They respectively denote momentum diffusion and pressure waves in the boundary.
So here still it's a boundary safety point of view.
This is the current and stress tensor of the boundary CFT. I'm doing an SOD minus to decomposition of these fields, which you are interested in the hydrodynamic limit, conserved objects.
So for CFT is necessary, or for the holography it's necessary, but if you just consider the QFT, do you
say again?
Is it necessary? Where do you need the CFT? I mean here.
I didn't need the CFT. So far I'm just so that's why if you noticed, I said like we motivate a formalism which at least in holography should work. So like we are whatever I'm saying here seems to be like true for general CFTs.
Okay.
But like why I emphasize holography is that from the bulk there is this second gauge invariance point of view which motivates that this decomposition is sensible. Right. So these are general statements about any field theory. For instance, like if you think about this JV part, which I call is trivially conserved, which I say is fast relaxing current. It's like the magnetically excited eddy currents in a metal, right? So when you use a magnetic brake, what you do is you apply magnet and trigger these eddy currents, which relax quickly and dissipate heat, and the brake indeed works, right? So it is in that way. It is yeah. You don't need a real CFT or anything to kind of these points chime well with any general system, right? Okay. So. Okay, so the idea then is to, once you realize there's an SOD minus to decomposition which is sensible, the idea is to we say that each such hydrodynamic mode, say these JS, JV, etc., is dual to a scalar master variable in the bulk. So we go to each of the degrees of freedom, and then say each of the degrees of freedom are dualizes to scalar fields in the bulk. So we don't work in the conventional, the familiar like Maxwell or gravity way of looking at these excitations in the bulk. It is because of certain subtleties, it is useful for us to go into some scalar degrees, which does away with all the gauge invariances and so on. We just dualize every degree of freedom to some scalar master variable. So like more explicitly, what I'm saying is you can write the bulk solutions to Einstein and Maxwell fields, some A mu and H mu nu's, this way, where these are the scalars, what I have labeled as phi d minus 1, 3 minus d, and so on, which then denote the vector, tensor, etc., the decomposition of the bulk Maxwell Einstein fields. Okay, and I have like kind of not explicitly written the scalar graviton sector because it's slightly involved. But most of my discussion will be based on these four sectors, and they will the general story and the lessons we learn are like applicable to the scalar sector as well. So the point here is the way to write these master scalars with these indices, specific indices and so on, is that you find a non-trivial relation between these sectors. The relation is that each of these effective scalars can be thought of as extremizing like an effective action for a dilaton coupled scalar. So if you look at this massless scalar action, which is the usual Klein-Gordon action plus some non-trivial dilaton, which we set to be e raised to chi s, which we set to be some fixed value r power m minus d plus 1. It is a one parameter family of massless Klein-Gordon actions, dilaton coupled Klein-Gordon actions, with just fixing different values of m like this will land you on the dynamics of these degrees of freedom. So hence so we call this m a Markovianity index. Just the value of m decides with which sector you're coupling to, because these d minus t and d minus 1 here were Markovian sectors, and the 3 minus d and 1 minus d were the non-Markovian sectors. Okay, the scalar effective field has slightly more involved equation of motion, action and dilaton and so on. It has some non-trivial potential and so on. But the rest of the statement is true. So what you find is in the Markovian sector, you notice that the bulk gauge fields were directly proportional to the scalar field. But in the non-Markovian sector, the bulk gauge fields are really the conjugate radial momentum of the non-Markovian fields, scalars. Okay, so that's one distinction you find, but it's a non-trivial statement that all these dynamics can be captured by a simple one-parameter family of actions like this. So motivated from the above examples, and based on the analysis of such generalized M scalars, because once you write this action, you don't need to be limited to the specific 4 cases of M's. You can study them for general M, solve it for once and all, and you realize that when M plus 1 greater than 0, these scalars behave like Markovian modes, which is true in these examples. Okay. And when M plus 1 less than 0, these scalars behave like non-Markovian scalars, non-Markovian degrees of freedom of the boundary.
Is it independent of the dimension, or?
It is, because the equation of motion depends on the dimension only via the redshift factor. There's a redshift factor, and it has some non-trivial depends on the dimension. The redshift factor of the blackbrane, which is F actually. Okay, but apart from that, this M is designed to cancel the dimension dependencies, in the sense that this root G is proportional to R power D minus 1, and this E raised to chi s actually cancels that, and so on. So finally, the only dimension dependence in the problem comes via the redshift factor, the dependence of this F on dimension. Yeah. So that's why, like, I don't specify the dimension in these discussions. So when M plus 1 greater,
the battery of this effective this dilaton. I mean dilaton action. Here you have metric. Is it what kind of metric?
I haven't written the metric, but it's a usual blackbrane metric where you
blackbrane. Okay.
It is there's not it's just a usual metric. Sorry, I don't have it written.
Okay.
Yeah. But it's just the fact that this F is this. So there's some. We work in ingoing coordinates. Okay, which I haven't emphasized till now. So that's why I'm using this V is my time. Okay. For some reason, we have to work in ingoing coordinates, which will be evident as I come to the Schwinger-Keldysh part. Okay. And the metric is just R square F minus R square F dV square plus 2 dV dr plus the plane dimensions plus R squared plane dimensions. So R square F is the G00 and F is some 1 minus 1 by R power D or something. Maybe I'm saying it, it's kind of confusing to listen. Sorry, I don't have it written. But it's just the usual blackbrane metric in ingoing coordinates. So the point here is that, so like this distinction I made about how the scalars appear in the gauge fields. So remember, gauge fields in their boundary limit becomes the sources of the boundary. So this statement about what is the source, what is the gauge field, whether phi or the conjugate moment of the phi, when you transcribe it to the case of the boundary operators, it flips. In that the boundary 1-point functions are given by the conjugate momentum of Markovian scalars, phi m, and boundary value of the non-Markovian scalars. Remember the sources were the scalars for the Markovian, but now the operators are the conjugate of pi m's for the Markovian case, and other way for the non-Markovian scalars. So analyzing this M plus 1 general M scalars, you see that for Markovian scalars, ingoing modes are non-normalizable, always non-normalizable. If you want an ingoing mode, it is always non-normalizable, implying they are triggered by boundary sources and quickly dissipate when sources are turned off. And the non-Markovian scalars, you realize that for some special ingoing modes, where you tune the frequency and the momenta, which is to say they satisfy your dispersion relation, you can have ingoing modes without any boundary sources. You can have ingoing modes which are normalizable. Okay, and then you realize that hence non-Markovian scalars can be thought of as characterizing your hydrodynamic configuration, where you don't have non-normalizable modes, which means you don't have sources in the boundary, but still you have some ingoing configuration in the bulk, which is to say that in the boundary you have fluid configurations, which is not really driven by anything, which is not sourced, but is just evolving in a dissipative fashion. Okay. So if you analyze these equations of motion, general M equations of motion, you find that pi m, the conjugate momentum, always have derivative expansion in terms of phi m at the boundary. And since, like I motivated, there's a difference in dictionary between what is source and what is operator in the non-Markovian and Markovian cases. This fact has a different interpretation in each of these cases. This is interpreted as a local expansion for the sourced one-point functions for the Markovian boundary operators, because pi m's are the Markovian boundary operators. It's a local expansion for the one-point functions for Markovian boundary operators and equation of motion for the non-Markovian fields. So to write it explicitly, you always get an equation like this. But in the Markovian case, pi m's are the operators. But in the non-Markovian case, the pi m's are the sources. Okay. So depending on that, this K gets interpreted in a different way. Markovian operators have no long distance correlations because the one-point function has some expansion in terms of the source, phi m. So because Km is interpreted in this case as a Green's function, okay, which you attach to the source and calculate the one-point function. And it has an expansion, which is the fact that Markovian operators don't have long distance correlations. They have like local expandable Green's function with some gap and so on. And non-Markovian operators have diffusive long-range correlations, because in that case, Km is the inverse Green's function. Because pi m in the non-Markovian case is the source, and this is an equation for the source, which is pi m, in terms of the operator phi m in non-Markovian case. So that's the sense. So Km is the inverse Green's function or some kinetic term in the action for the non-Markovian scalars, which when acted on the field gives you the source, appropriate source. This is a dynamical equation, hence. And then like coming back to the setup we were motivating before, the Wilsonian FT theory, you realize that I motivated that you can indicate out the fast Markovian modes and retain the non-Markovian modes in your description. So the right boundary condition is to say that the Wilsonian EFT is parameterized in terms of the sources of Markovian modes and the effective scale at the field values in the non-Markovian case. So you realize you have to fix the boundary operators with non-Markovian behavior and boundary sources with Markovian behavior. So I'm summarizing that boundary condition in this table, which is Wilsonian EFT. The boundary condition for Wilsonian EFT is to fix a boundary source for m plus 1 greater than 0 or Markovian sector, and one-point functions for m plus 1 less than 0 or non-Markovian sector. So this is the Markovian sector, this is the non-Markovian sector. The first line shows what are the usual ADCFT boundary conditions, the GKPW boundary conditions, which says which is fixing the source for every sector to calculate correlation generative functions. So in that picture, what we end up doing is like you fix the phi m, the source in the Markovian, and pi m, the source in the non-Markovian. But the picture we are motivating is that you have to fix the operator in the non-Markovian, which is phi m, and source in the Markovian, which is phi m again. So in this picture, it is like you have to fix phi m in all cases. But whether it is operator or the source gets reinterpreted because fundamentally because in the bulk solutions they appeared in a different way, like this. Okay. So a cute thing you realize once you implement this is that naively, if you start with the GKPW prescription, which is calculating the generating function of the CFT, and say you wanted to now transcribe it to a effective action for the non-Markovian scalars or operators. In field theory, as we usually do, you have to perform a Legendre transformation, which goes from the correlation generative functional to the effective action. Okay, but and in the gravity calculation, it is a statement that when you want to change boundary conditions, you have to add boundary terms, which implement the boundary condition change so that the variation principle is correct and sound. once you start trying to rewrite this problem in terms of the scalars, that is once you convert the gravity action, the Einstein-Maxwell action into scalars, you realize that by on the way to writing this form of the action, you end up imposing all these boundary transformations naturally. So in some sense, gravity already knows that the right Wilsonian object or the right object to look for is a system where you have this effective action, and this effective action naturally has Dirichlet boundary conditions for phi m. So kind of gravity already predicts that for general M, whether it's Markovian or non-Markovian, you have to impose Dirichlet boundary conditions for phi m, which is fixing phi m, and which is in fact what I have written here, that you have to fix phi m in all cases. This is the last slide from my first part of the talk. So I want to stop for questions.
How about the other, like a Riemannian boundary condition, Neumann boundary condition, or?
Say again. This is actually in fact Neumann boundary condition. So the GKPW was Dirichlet boundary condition, but written in terms of gauge fields.
Yeah.
Right. That's why.
Wilsonian case. So what if you? I mean, it's a funny question, but here you mentioned that with the gravity side, they know that this Dirichlet boundary condition is more natural, so that it is natural for the Wilsonian case.
Sorry, say again, or what? I couldn't hear.
Here you mentioned your conclusion. As far as I understand, the conclusion is that the Wilsonian case naturally have this Dirichlet boundary condition.
Dirichlet boundary condition written in terms of these fields.
Yes.
So if you were working with the original Maxwell-Einstein gauge fields, it is in one kind of gauge fields you put Dirichlet boundary condition, which is the Markovian, the usual boundary condition, which generates correlation function. But in the other part of the gauge fields, which dualizes to non-Markovian operators, you have to put Neumann boundary condition because you want to fix the operator. But we have in the bulk, the way we do it, we have rewritten all that Maxwell-Einstein dynamics in terms of effective scalars, in terms of which this separation is no longer there. In terms of the scalars, it's Dirichlet boundary condition for both. But if you are written in terms of gauge fields and Einstein-Maxwell fields, like the usual gauge fields, you would have had to carefully do Dirichlet for half of the fields, Neumann for the other half of the field. But if you rewrite the dynamics as scalars, it's Dirichlet for all of them. That's what we are saying. For the Wilsonian boundary condition, right? But if you rewrite the GKP, the usual boundary conditions in terms of the scalars, it then becomes mixed. So the statement is, if you want to just understand the GKPW boundary condition, the right kind of field variables is the usual field variables, Einstein-Maxwell gauge fields. But if you want to understand the Wilsonian boundary conditions, the nicer variables is these scalar variables, where you have Dirichlet for all. Okay, maybe I should summarize like this. The Wilsonian boundary conditions, when written in terms of these effective scalars, is Dirichlet for all. And GKPW boundary conditions, when written in terms of the original gauge fields, is again Dirichlet for all. But yeah, that's a statement. So the point here was to once you think about non-Markovian Markovian separation, you go to SOD minus 2. You naturally get led to the scalar decomposition V motivated. And then the nice boundary, the correct boundary condition or the physically motivated boundary condition is Dirichlet for all these scalars. Yeah.
Okay, thank you.
So if there are no more questions, we will go to the next part of the talk, which is a summary of Schwinger-Keldysh path integrals. Okay. So the point is, open systems are described by reduced density matrices, right? So you have to now think about the field theory dynamics is not described by a conventional path integral where you think of some transition amplitudes from some initial state to final state, but the field theory dynamics has more general correlators where whose correlation generating functionals are defined by this object, which I call the ZSK, Schwinger-Keldysh generating functional. where you can apply operators on the density matrix as it evolves on either side of the density matrix. Like, so this is the some unitary which you can differentiate with sources to apply operators on the left side of the density matrix, and similarly on the okay, this I'm calling the right side of the density matrix, and similarly for the left side of the density matrix. Okay. So this is the statement that these operators act on the ket density part of the density matrix. These operators act on the bra part of the density matrix. And alternatively, this generating function can be thought of as an evolution on a closed time contour. Sorry, where you think of this is the density matrix as having a ket part which is violet and bra part which is red, and then the ket evolves as in time, and then you as after some maximal time you evolve backwards and match with the bra. So come together, you can think of this as the ket plus bra system, ket times bra state or a mixed state evolving in time. And this final matching here then is simply this tracing action where you identify the ket and bra, because a trace is just identifying ket and bra, right? And so then you realize that path integrals, since they should calculate general time ordered correlators, the fields on the ket part of the evolution is time ordered, or correlations on the ket part of the evolution is time ordered, and the correlations on the bra part of the evolution is anti-time ordered. And the ket, and this is the reason I call ket the right and the bra the left, because it evolves towards the right and comes back towards the left. And if you're interested in the thermal initial state or something, we know that the thermal initial states can be thought of as prepared using a Euclidean evolution over a beta circle. So then you can add a Euclidean segment to this path integral where you identify these dots matched with the colors and so on. So if you do an additional density Euclidean evolution and attach it, complete this bent contour to a circle with a Euclidean circle, you end up realizing a thermal initial density matrix on these points. So that's like a lightning review of this Schwinger-Keldysh. If there are any questions, I can take them. So to summarize, it's a path integral formalism which tracks the evolution of density matrices rather than pure states. So then a couple of points to note about the formalism. One, there's a doubling of the operator content, because for every field in the original theory, you now have a copy of the field. At an instance of the time, you have a copy of the field which acts on the ket space and which acts on the bra space, the right and left copy. Okay, and then like I said, the path integral calculates contour order correlators. The right fields are time ordered and the left fields are anti-time ordered. And the tracing is implemented at a future time where you identify these degrees of freedom. So this is a setting of notation. You can think of and take the log of this generating function and call it an action, a Schwinger-Keldysh action, which I write like this. Which it's a function of the right and left sources, and it will have a structure something like this. There will be an independent function of the right sources, same function of the left sources but subtracted, and then there's a mixed function of the JR and JL, which I call the Schwinger-Keldysh influence functional. Okay, the IF stands for influence functional. The point about making this distinction is that suppose you want to now study an open FT field theory in Schwinger-Keldysh, but in this format, right? What you do is say you have some system, some bar degrees of freedom, which you can call O, some probe degrees of freedom phi, and your aim is to study the coupled system, but then integrate out the bath. Okay, so say the coupling between the bath and the probe is like via some. So let's say this is the bath and this is the probe. Say it's coupled linearly, so there's some phi O coupling. Then you can integrate out the O, which is essentially the calculation where you calculate the generating function of O with sources set to be phi. Okay, so when JR and JL are interpreted as fields of the open system, the probe system, S influence functional is the influence functional SIF is the influence functional generated by tracing out Barth fields. So the statement is, if you have a unitary system with both the probes and the Barth evident, you only have terms, you don't have any mixed terms which identify JR and JL. That's why you can study it as a one copy calculation like we usually do, where you just look at just the R part or just the L part. But the statement is, once you integrate out this phi O and integrate out part of the fields, you end up generating these mixed terms in the action, which says, since O has been integrated out, it says the phi R, the probe R and probe left fields are coupled. So the open systems have couplings between the degrees of freedom acting on, or the fields acting on the Ket and Bra spaces. That's the statement. And then there are consistency conditions and so on, which says that this open action indeed came from a microscopic unitary action, which is a statement that if you put JAR and JL to be identical, the partition function, the generating correlation function correlation generating functional should reduce to identity, which is just a statement that if you put JR equal to JL here, since the density metrics, these are both unitary and unitary daggers, the tracing will cancel them and the generating function just reduces to 1 because trace of density matrix is 1. And like translated to the case of this Schwinger-Keldysh action, it just says if you put J and identify JR and JL, the action should vanish. Yeah. So that's partly also motivates the structure. That there is a part which manifestly vanish because it's some function of the R subtracted with the function of L. But then there is a mixed functional, and hence the mixed functional should vanish by itself when you identify sources. If there are any questions, like, so that's all I have about the Schwinger-Keldysh formalism. And now I will go to the gravity way to think about it. And if you have any questions, you can take it now. Okay. So now let's talk about how to think about such calculations, such Schwinger-Keldysh path integrals of the boundary theory in gravity, right? So from ADCVT, we say, if you have a CFT on some manifold M, the bulk dual is the gravity calculation in all manifolds which have, so if you have CFT as del M, on CFT on the manifold del M, the bulk calculation is all gravity calculations with del M as a boundary, right? So you have to consider the bulk gravity action, gravity path integral in all manifolds which asymptote to the CFT manifold. Therefore, the relevant gravitational saddle in our case should asymptote to the field theory Schwinger-Keldysh contour. And now this is like a confusing setup, right? Because our Schwinger-Keldysh contour had a double CFT, and it's a thermal state implemented via some Euclidean initial segment. Now you have a bulk saddle which should have two Lorentzian asymptotics, one thermal initial source dense asymptotic, which is like a Euclidean black hole and so on. So it's some if you really take this statement strongly, it's confusing. But so these guys sometime around 2005 gave a cut and glue construction for a mixed signature saddle. They said, okay, what we're going to do is we'll take the Lorentzian black hole, two copies of it, and in fact only the exterior, say this pink shaded region here, glue them along their horizon, and then we'll also attach a Euclidean cigar at some initial time slice, and we will construct some geometry like this, where you have a thermal circle in the initial time and some folded time contour in the boundary and so on. So what they managed to do is they were able to motivate the general ADS-CFT rules for thermal retarded propagators and so on from some construction like this. But the fact is, though it looks plausible and nice, it is very hard to work with this prescription, because mainly due to the fact that once you glue the horizon and you have to correctly account for the Hawking radiation from the horizon and so on, which is typically singular at the horizon, unless it's very hard to come up with a nice gluing procedure at the horizon. So they were basically not very, they were not very clear about what is the glowing prescription here, which gives nicely behaved Hawking radiation at the horizon. But their argument was fine for the time, because if you want to calculate 2-point functions in ADS-CFT, it's actually a boundary term calculation evaluated on the on-shell solutions of the bulk action. You don't have to really do a Witten diagram calculation or anything in the bulk. You don't have to integrate anything in the bulk. So this subtlety kind of was like swept under the rug, right? And but once you come to the point where you have to calculate this non-trivial effects of Hawking radiation interact with ingoing radiation and so on, like I was motivating before, their construction becomes really ambiguous, because you have to be careful about how to correctly, nicely work with Hawking radiation, regularize it at the horizon and so on. But so we will work with a prescription which came up recently by these guys, Glorioso, Crossley, and Liu, which kind of gave a nicer saddle, which morally looks like this, okay, but which has a nicer horizon structure. And I'll try to explain their prescription now. So this is the Crossley, Glorioso, Liu prescription for Schwinger dish black holes. So their statement is this: remember, if you work with ingoing coordinates, quasinormal excitations, or the ingoing modes, are regular as functions of radius at the horizon. But it's only the Hawking modes. So specifically in ingoing coordinates, the ingoing functions are regular at the horizon, but it's only the Hawking modes which suffer from irregularities or singularities. Hawking modes, in fact, suffer from some branch cut singularity. They are they diverge, and in fact, they have a branch cut as function of radius. So now they're saying, okay, their prescription is to do this. To resolve singularities, naively deform the radial coordinate around the branch cut. So if you forget that it's a real radial coordinate is a ray which starts from the horizon to the boundary or something, forget that. Think of it on a complex plane, and just like how you resolve singularities when you do an integral, bend the radial coordinate around the branch cut, ending up with the geometry with doubled asymptotics. Because you have a branch cut starting from the horizon to infinity, you kind of bend it around. So this is a picture. And the statement is, if you bend the radial contour around the branch cut and end up with the doubled asymptotics geometry, standard rules of ADS-CFT on this geometry yields Schwinger-Kelvich correlators. Okay, so the picture is this. This is a slice of the one constant time slice of the blackbrane, but in ingoing coordinates, which is very crucial for the statement that in fact the ingoing solutions are regular. And all the irregularities come from this branch cut is really the branch cut of Hawking modes as a function of R. And they say if you study, if you think that the bulk saddle has this analytic structure, then you just need to impose the usual GKPW or whatever boundary conditions you want to impose. And the correlators generator will have the correct analytic structure of thermal correlators, which is statement that they have KMS correlations and all that. They should satisfy all the correct Schwinger-Kelvich structure of the action or correlations or whatever. Sorry, correlations or whatever. In fact, you can go ahead and we showed that if you study but then the question is okay, you can do this calculation, and then how does it work for all kinds of fields? Does it work for spin fermions? They kind of worked out, showed that it should work for bosonic fields. But now the question is, how does it work for fermionic fields or something? So we show that if you study fermionic fields, what happens is that when you compare solutions across the top and bottom of the branch cut, what happens is that fermionic fields, one bosonic fields have a Boltzmann suppression. There's a relative factor. Ingoing modes match because they are analytic at the horizon. If you match ingoing solutions here and here, they match. But outgoing solutions have branch cut singularity, so they have some non-trivial monodromy. The monodromy is exactly given by Boltzmann factor. Okay, and that's how this prescription implements thermality of correlators. By implementing that, Hawking modes have a Boltzmann factor monodromy. And we showed that if you study fermionic fields carefully, they have an additional monodromy factor which depends on the spin. Okay, so which kind of changes this Boltzmann factor, gives an additional minus sign to this Boltzmann factor if you have half integer spins. Okay, so naively you can say that if you replace the e raised to beta omega in a Bose-Einstein distribution with minus e raised to beta omega, it converts to something like a Fermi-Dirac distribution. Okay, so that's the way holography actually implements thermality by in this way of looking at it. That if there are additional spin-dependent monatomics which kind of change the Bose-Einstein distribution to Fermi-Dirac distribution, which is like, if you take a step back and think about it, it's completely non-trivial that now you do a classical calculation in the bulk and end up reproducing quantum statements like that the fermions should be like, like Fermi-Dirac distributed and so on. Somehow the bulk, the nature of gravity solutions, the fact that they have this branch cut or the singularity and so on, once interpreted as boundary correlators, implements all those structures. So this. Go ahead.
Maybe you have a slide or not, but if you look at this, you can have many like contour. There, like the two here, you consider two single Kellish, like a left
one
and
time
right,
fold. One time fold.
Yeah,
that's what you mean.
Yeah, one time fold. Yes, but you can consider k time fold.
Right. So which is an interesting. Yeah, it is an interesting point, and like we try to like construct something like this, some nice analytic prescription like this for such contours, which didn't really work out. And in fact, you can check some work Mukund was doing. Mukund was trying to construct these real-time replica saddles of gravitational path integrals to understand these island kind of pictures in real-time way. So I think they also try to do this OTO prescription because, and it doesn't quite work out. So the short answer is no one knows like how to effectively construct these bulk saddles which give OTO correlators. Yeah. So one way to say it is that like already your usual black holes, if you consider some eternal black hole, it comes with the second asymptotia, right? There's a thermofield double picture. So some sense like one fold contour is kind of easier in gravity rather than k-fold contours. That's one way to say it. Because thermofield double is closely related to Schwinger-Keldysh. Right. Okay, so this is some consistency checks you can make sure. So okay, one thing I want to emphasize is this is a prescription, right? It's not derived from a fundamental statement in gravity or something. And we don't fully understand why such an analytic continuation should be the right way to think about this or something. But the thing is, you can calculate correlators and check they have the correct KMS structure, they have the correct Schwinger-Keldysh properties, and which they do for general spins and so on. And there are some more consistent conditions you can check. You can argue that even simple Witten diagram calculations, like some contact interactions in the bulk and so on, if you evaluate such diagrams and calculate non-interacting terms from the bulk, or the interacting Schwinger-Keldysh path integrals in the bulk, they also will satisfy KMS and they will have some nice structure and so on. Maybe like because of time constraint, maybe I won't explain this too much. And another point is that you can extend this contour prescription to rotating and charged blackbranes. Okay, and there also it seems it works. It gives the correct correlators even when there's a charge in the bulk and rotation in the bulk and so on, which in the boundary correspond to specific chemical potentials for the rotation and some charge density and so on. Okay, so this is something. So this is now like okay. If there are no questions about this saddle, this bulk Schwinger-Keldysh saddle, I will move on to the next part of the talk.
Yeah, go ahead.
Okay. So now let me just briefly talk about this toy model of deriving nonlinear Langevin equation from the bulk by doing this kind of calculations. Okay. So basically the question is like I've been talking about Schwinger-Keldysh path integrals and so on. I seem to be doubling degrees of freedom and so on. Like how do I interpret this? How do you make sense out of it? So the simple way to make sense out of the Wilsonian EFT picture we are motivating is by mapping it to a stochastic differential equation. So the statement is there's a clean procedure. There's a clear procedure to map Schwinger-Keldysh actions, the kind of things I've been like talking to you about, to stochastic differential equations. And as a toy model, I will discuss how this is what it gives for a Brownian particle. So as a toy example, consider a particle probing the plasma again, and the bulk dual is so this is trying to understand a Brownian particle moving in the boundary CFT in the CFT plasma, and trying to understand the Langevin equation followed by the Brownian particle. And you can calculate it to the next order and make it a non-linear Langevin equation. And in the bulk, this calculation dualizes to a string starting from the boundary at the location of the Brownian particle, but then extending all the way to the bulk blackbrane and dipping into the horizon. So what happens is like the energy of the Brownian particle can dissipate into the blackbrane because like some quasinormal kind of excitation. And then the blackbrane really Hawking shakes the string. It really Hawking radiates string modes, and then these fluctuations travel via the string, reach the boundary, and appear to be the Brownian noise hitting the particle, right? So the bulk dual is a string dipping into the blackbrane horizon. And Langevin equation for the Brownian particle can be derived from the bulk dynamics of the Brownian string, which is the statement that you just evaluate the number go to action or something. And then you don't need to restrict at the linearized equation of motion. You can go to the nonlinear level and in fact calculate the corrections to the Brownian, the Langevin equation. So the first non-trivial correction seems to be of this form. So there's a usual Langevin part, there's an acceleration, there's a drag gamma, and then there's some stochastic noise with some probability distribution. But now the non-trivial corrections, first non-trivial correction is that the drag itself becomes noisy. There's a thermal jitter to the noise, to the drag, which is characterized by the same noise as suppose, okay? And it's characterized by some coefficient zeta gamma. And then at the same time, the probability distribution of the noise lifts from a simple Gaussian to a colored Gaussian. There is some frequency dependent Gaussian part plus a non-Gaussian part. There's a fourth order cumulant to the probability distribution of the noise. And so earlier you in the usual Langevin equation, we argue that for consistency, the gamma for the thermal consistency or whatever, or the fluctuation dissipation relation, which was motivating in the introduction, the dissipation drag and the variance of the force F square should be related like this. This is the usual fluctuation dissipation relation we learn. But the statement about this generalized Langevin equation is that now the non-Gaussianity in the equation of motion, the non-Gaussianity in the dissipation, which is zeta gamma, and the non-Gaussianity in the probability distribution, zeta n, should be again related by a fluctuation dissipation relation. Okay, so this is a naive honest calculation for the bulk using the Schwinger-Keldysh prescription and so on, where you evaluate the nonlinear corrections. But it has been independently motivated. This was independently motivated before that the first corrections should be of this structure, and there should be a fluctuation dissipation relation of this kind and so on. Just from the bulk, just from field theory calculations, okay, by these works, which are work since you know this is work by Vidisha, Soumyadeep, and Loga, and they had independently motivated this from field theory by studying particles coupled to a weakly coupled bath and so on, and doing a computation in field theory. So the statement is one way to think about the consistency of the Schwinger-Keldysh prescription is that in the simplest case you can check it reproduces this non-trivial structure, okay, which is a Witten diagram calculation of the bulk because you are doing interactions in the bulk and so on. But for the string mode, yeah, and the lesson we want you to take away from this is that the kind of calculations we are trying to do is trying to understand generalized. So now remember, this is an equation of motion for the Brownian particle, and which I have written as a Langevin equation and so on. So similarly, there's a story where you have a fluctuating hydrodynamics where you have a fluid equation of motion, say the Navier-Stokes equation, but now it is getting corrected with noisy forces which drives the fluid, and the force has a well-structured probability distribution, and the probability distribution is intimately related to the dissipation constants appearing in the fluid's evolution, and so on. So that's one way to see a physical picture of all these calculations. apart from some abstract Schwinger-Keldysh field theory for the fluid. So if you have any question from this, I'll take it, and then I'll summarize.
Sorry, I already lost the. So here, this is toy example, and then you solve this stochastic.
Say again?
What's the conclusion of this slide? I already.
The conclusion of the slide is that like you have a Schwinger-Keldysh description of, okay, from the bulk you will end up deriving a Schwinger-Keldysh action for the Brownian particle. Yes. But there's a well-defined procedure as laid out by these guys to convert that Schwinger-Keldysh action to something we understand better, which is the Langevin equation. Okay, and a noise stochastic noise for the Langevin equation and so on. So the statement is part of the Schwinger-Keldysh action gives you this equation of motion, and the other part of the Schwinger-Keldysh action encodes this data. What is the probability for the noise? Schwinger-Keldysh action includes both these data.
So you mean the bulk side is already known, but from the Schwinger-Keldysh you can systematically derive this kind of.
Yes, from the Schwinger-Keldysh you can systematically derive the Langevin equation for this general systems. The Langevin system for the general system, like fluid or something, the analogous object to Langevin equation, Langevin Navier-Stokes. I don't know what to call it now, but you can derive that object, and there's a systematic way to do it. But the natural way to, as a theoretical tool, the natural place to compute these things is to do a Schwinger-Keldysh path integral.
So here, this result might be independent of holography.
Yes, exactly. So this result was derived earlier by Bidisha, Saumedeep, and Loga. This kind of results, some variants of these results, and so on, and especially this new non-trivial fluctuation dissipation relation. The statement is, even if you didn't know that all that can be done carefully from doing Schwinger-Keldysh path integrals in the field theory and so on. Okay, just naively believing this bulk Schwinger-Keldysh prescription gives you these answers, and it seems to be consistent with these field theory results, which is in fact a way to argue for the consistency of this prescription, because, like I said, it's just a prescription which we don't know where it really comes from. Right? Okay. There are no more questions. I'll summarize. So I motivated a formalism to distill out fluid modes of different hydrodynamic natures and introduced alternate boundary conditions appropriate for the Wilsonian EFT. Then I briefly explained Schwinger-Keldysh path integrals, and then I motivated a gravity construction which implements the same. Then there are a couple of immediate future directions, right? So one thing is that, like, no one has really studied interactions in the Schwinger-Keldysh gravity saddle, and so the only papers which does this paper where we do the Brownian particle case, and there's another paper by Chandan, who was a student here with Loga and then moved on as a postdoc to Witwatersrand. Chandan, Mukund, and Loga. They have a calculation where they study phi n, the arbitrary phi n scalar models in the bulk, and then they derive the generalized fluctuation dissipation relations for all those scalars in the boundary. Okay, and so that's one Witten diagram calculation. So these are the only two instances of interactions calculated over the saddle. Okay, and both these cases are limited to contact interactions. They don't really study exchanges or loops or anything in the bulk. And it is like really crucial to check that, because we don't really seem to know how to derive this prescription, to check that these such general Witten diagram calculations yield consistent answers. So that's like this part of the future direction, that to understand exchanges and loops and follow through that, check that they actually satisfy Schwinger-Keldysh consistency relations. And then then this loop part kind of leads us to the second motivation, second future direction, which is to understand long-time tails in the fluid, which is a statement that related to the sickness I mentioned in the motivation, that once you start accounting for fluctuations of the long-lived fluid modes in the system, it kind of says that the correlations you expected to decay down don't really decay down fast. They will develop long-time tails and so on. because there are fluctuating degrees of freedom. There are long-lived degrees of freedom which are now fluctuating. So to understand such setups, such effects, like consistently from the gravity. Okay, so that's the second direction here. So then there are these. Then we have to think about how to understand the saddle, the Schwinger-Keldysh bulk saddle. We have to derive the saddle, and then maybe that would also inform us how to describe it away from equilibrium. Because if you remember, like I motivated the saddle as a simple complexification of the usual ADS blackbrane, which is just an equilibrium configuration, and then you are only perturbatively studying excitations around it. But you could think about really highly non-equilibrium configurations of this field theory, and hence highly non-equilibrium configurations of the bulk or of the blackbrane, whatever it means. So maybe like so these directions point to the fact that like we have to. There's a regime where you can think about some non-equilibrium blackbrane configurations and try to understand their dynamics and so on, not just perturbatively. Yeah. So that's it. Like, thank you for your attention. Yeah. If there are any questions, yeah.
Thank you very much. Please ask a question.
I have some questions. My first question is, in your Langevin equation, so if I consider the holographic dual, what is the origin of the noise from the Hawking?
That's right.
Yeah, can you identify, so what is the, how can I understand the emergence of such noise distribution from some Hawking?
Okay, one simple way to do it is that you can, in the bulk you can calculate these effects. You can, if you believe the dictionary that there is a Brownian particle in the boundary which dualizes to string, you can now you can study the string dynamics in the bulk. There will be some leading order quasinormal kind of excitation of the string which dumps energy into the blackbrane. But then a consistent bulk calculation would ask you to also include the Hawking radiation of the string excitations. And then it's just a matter of checking that you do that calculation and end up deriving. So forget about interactions, forget about this non-Gaussianity. But if you consistently do a linearized calculation with Hawking modes excited, you will end up deriving this noise. So this is a standard ADS-CFT computation from 2009 or something, where you study Brownian strings and show that you can derive Langevin equation for the particle. So that's one way to, that's one simple way to motivate Hawking radiation is really the dual of the noise. But I mean, then it also helps to remember that Hawking radiation has a thermal occupancy and noise should have thermal occupancy and all that.
So how can I see such information from this Langevin? So gamma is proportional to T?
Say again?
Gamma here, So F square, so gamma is, so how can I see some temperature, I mean, some, so black body, thermal radiation property, gamma is proportional to T?
Yes, like, so this is the statement, right? I have like, these are nominal symbols here, but like these F squarens and gammas, you can calculate from the from ADS-CFT, and then you'll see that they are proportional via this temperature. So maybe I missed to mention beta is inverse temperature.
Okay, I see.
Beta is inverse temperature. So and MP is the mass of the Langevin particle. So I have like normalized the mass out, and you will see these relations are satisfied.
I see. Then let me ask more elementary question. So will you explain again? So how the Schwinger-Keldysh correlation function can appear from some such holographic dual construction? So simply, I just my understanding is very poor, so I want to listen again. So your explanation.
Sure.
For the holographic dual. Sorry.
The holographic dual. You mean this slide, no?
Yeah, exactly. Yeah.
Right. So I can explain the prescription. The prescription is to like the prescription is okay. First of all, there is a gravity saddle. There is a space time where you do ADS-CFT calculations with ADS-CFT boundary conditions interpreted in the usual ADS-CFT way. There is a gravity saddle where you do that calculation and you end up deriving Schwinger-Keldysh correlators. Okay, you end up deriving some correlations correlation functions of the boundary from ADCFT calculations.
Yeah, I get
And-
the message itself. So yeah, I want so maybe one slide before. So you about this So will you explain the right? So how can I obtain some So Hawking. So for the right hand figure, will you explain more of it? So simply I didn't understand it very well. Yeah, sorry.
This picture is a cartoon. So this is not a picture very evident from the way we do implement these calculations. This picture is mainly here because this is a picture motivated by these guys where they cut and glue blackbranes of different signature. So you impose junction condition and so on, and then glue some Euclidean blackbrane to two exterior Lorentzian blackbranes. By exterior, I mean this region in the Venn diagram, right? So this we don't have much to do with, like we don't talk about it much, and this don't really play much role, this picture itself. But the main thing is that this prescription is a description of the bulk geometry, where when you do calculate correlation functions and do a GKPW prescription and so on, gives you the correct Schwinger-Keldysh correlators. So maybe I missed to emphasize there are two boundaries, and each boundary corresponds to the left and right legs of the Schwinger-Keldysh contour. And then you can insert fields here or here, just like you do in ADA-CFT, which is interpreted as fields acting on the left or right of the CFT density matrix and so on. Okay, so that's the picture. And this slide was about describing that saddle. That the main thing being you have to work in the ingoing coordinates and impose. Think of the radial coordinate as a complex contour rather than just a real ray from RS to infinity. Yeah. Does that answer your question?
Yeah, you answered, but but still my understanding is not satisfactory for me. But anyway, yeah, okay.
Okay.
Thank you. Yeah.
Sure. Thanks. Thanks for the question.
Is there any other question?
Hello.
Hi.
My name is Tuna, and I'm at APCTP, and I also spent some time about this Schwinger-Keldysh stuff. And firstly, thank you for this very clear and nice talk. Maybe I can give. Okay, I first maybe give some comments about Kiseok's questions. Then I will ask you two questions about. I mean, my understanding about this prescription is kind of a bit more intuitive, and probably we are not speaking same language. But about this question about how can we understand this not Honglu's prescription but the previous prescription? Actually, I think Kiseok, you can think in this way. I mean, just this close time contour, and imagine what Akhil shows. I mean, just in field theory. I mean, you are just having this close time contour and embed it to the bulk. And this is just that geometry. I mean, roughly. I mean, you need to associate each rail segments with the Lorentzian manifold and each imaginary segment with the Euclidean manifold.
I see. Then the question is how the Hawking radiation is involved in this kind of geometry.
Akhil is giving very rigorous definitions, and mine is again kind of a bit more heuristic. I mean, I think you can think in this way. Normally in holography, when you are doing any calculation, quasinormal mode calculation, then you are mostly just taking infalling boundary condition on horizon. Yes. And in this case, there is no boundary condition on horizon, which means that you are not dropping outgoing modes. And this outgoing modes is something radiates from black hole. So it is related with the noise. And another issue is he also has some very nice papers about more complicated systems than Brownian motion. I mean, and it is more clear in this context because, for example, in diffusion, then these IR degrees of freedom are just the symmetry parameters. I mean, it is really natural to define in this way because in the end, these IR degrees of freedom, equation of motions of them should satisfy continuity equations, and it is directly correspond to them. And okay, now my questions. I really wonder about your comments about this long tail, and also the other exciting issue about this non-equilibrium, rerun non-equilibrium cases. I mean, for example, what will be the geometry in this case? And I just wonder about your comments, and I would be happy if you can elaborate.
Yeah, okay. The short answer is it's not okay. The long-term tail is like a story that like if you look at correlation functions, say of current correlation functions or something, they have long-term tails which don't like decay for soon as you expected them to, and they decay more slowly, and then in fact they're in the frequency domain or something, they have like non-analytic behavior, right? They have fractional powers of the frequency and so on, which once you incorporate such effects into the hydrodynamic description, it kind of kills it makes your theory sick. And then there is a story about how you can, some idea people have about how to capture those effects from the bulk, right? Which was done by Karen Hoare and Seremi and so on. The statement is like in the bulk, to see these effects, these are 1/n suppressed effects, and to see these effects, you have to really do loop calculations, loop contributions to correlation functions from the bulk, which they kind of do. They do some hand waving and so on, and then they have some answers which reproduce these long-term tails. But the crucial thing about all these pre-CGL, pre-closely glorious real-time computations in ADS-CFT is that the horizon and the near horizon Hawking radiation is like a mess to deal with. So they also have to think about some effective horizon degree of freedom and all that, if I remember right, to kind of extract out these long-term tail effects. So the advertisement here I'm giving is that this prescription is kind of clean to work with. You just naively impose this contour analyticity, and you can do you can just naively integrate a Witten diagram calculation and extract these answers, right? And then one of the key points were that, like, at least for contact interactions, they were giving the correct answers. Now the question is, does that structure, the correct string structure, the KMS conditions and so on, do they survive once you go to loop calculations and so on?
Yeah.
Or maybe one question is to ask, do they survive once you start correcting for the geometry, once you start accounting for back reaction and so on? Okay, so that's the kind of statements I'm like kind of pointing towards here. But you really think about exchanges and loops, back reaction, and then what are the physical diagnostics, right? Physical diagnostics for the loop effects in hydrodynamics say is the long-term tails. So that's this part of the comment. Okay, that's all I mean by writing this here. Then the away from equilibrium, like you said, I don't have anything nice to say about it. It's like it's a confusing question. Even this is a confusing question, and the start would be to either derive the saddle or like start deforming the saddle by studying gravity perturbations on the saddle and so on, and trying to understand these structures, like I said before. So I don't have anything much to say about the away from equilibrium direction.
Yeah. Do you think that this closed time contour will work, or probably it needs to be modified?
Away from equilibrium in the field theory is really okay. The only way to think only sensible way to think about it is via closed time contours, right? Because you have to go Schwinger-Keldysh. Away from equilibrium is a statement that you don't have a diagonal initial density matrix and so on, right? So you necessarily land on Schwinger-Keldysh in the field theory, pretty evident. But now, now to realize it in holography, right? Realize a black hole configuration where you have an away from blackbrane, and you have to have space times which correspond to left and right part of the CFT evolution and so on. And you have away from equilibrium. I mean, you have to imagine a horizon away from equilibrium. Like you have to glue things at. I mean, it's a very ambitious thing to
Yes.
think about.
Yes.
So I don't have anything to say about it. Right?
Yeah.
Thanks for the question.
Okay. Thank you very much. It was very clear and nice. So yeah, and it was really nice to meet with you.
Thank you.
Thank you.
Is there any other question? If not, let's thanks for our speaker for very nice talk.
Hey, thank you guys for having me also. Okay.
Thank you. First.